Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, let's get started. So it's my pleasure to welcome Gary Wasserman, who's finishing up his PhD from UC Davis. And he's going to tell us about some work he's done for his PhD on engineering secure web applications through a combination of static and dynamic analysis techniques to prevent cross-site scripting and Sql injection attacks. Gary?
All right, thank you. Well, my interest is to find principled solutions to practical problems. And so I know Ben's been doing a lot of work in this domain, but also web applications have been the domain that I've been working in. And a reason that I'm interested in them is, one, they're pretty new. So, you think 10 years ago, most of this stuff wasn't here. But also, they're all over the place. And not just geographically, because you can certainly get to them anywhere you've got an internet connection, but they touch so many domains as well. So you can file taxes online, you can do web-based email, you can apply for college online. There's all sorts of shopping and social networking and banking, all these things that touch the daily lives of many people and handle information that we'd rather not have made public. So to introduce this discussion, let me give the basic architecture for these things. So at the front end, you've got this web browser, which functions as the user interface. And through that, the user provides some input to the application server, which will then take that and typically use it to produce a database query for the backend database, which manages the persistent data. And then there's some result set returned, and based on that result set, perhaps some web page comes back to the user. So what this presents is a big challenge. It's a challenge to write these things correctly. It's a challenge to check that they've been written correctly. First, because they're distributed and dynamic. So the entire code doesn't exist in any one place at any one time for any one entity to regulate. It's being generated on the fly, and it's distributed over multiple layers. And then the application server has to do input validation. It's got stuff coming in, and it uses that stuff to produce output, which will get interpreted. So it has to check it. Then in the back, we've got what's known as the impedance mismatch. And basically, the idea there is, with databases, parallelism is competition, whereas with applications, it's an opportunity for cooperation. And so there's this sort of conflict of interests and goals there. Then over here, there's this many-to-many relationship where even within one browser window, you can connect to many servers, especially in the context of mashups. And one server certainly manages connections from many clients. The boundaries between the user's desktop and the web are increasingly being blurred. And then the protocols used to communicate are very low level, but people try and write very rich applications and rich interfaces over them. So that introduces, again, many opportunities for errors. Now, my work is focused on input validation. And some big instances of this problem are SQL injection and cross-site scripting. And I'll say more about those in a bit. But basically, what I aim to do here is to characterize what is an attack, what is normal usage. And then based on that definition, how do you enforce at runtime that malicious behavior is not allowed? And how do you check code statically to know whether any of these attacks are possible? Okay, so let me just say a little bit more about why the problems are important. And I may be preaching to the choir here, but I think it's interesting either way. So this is a graph showing percentage of vulnerability reports from 2003 to 2006. And these 5 that I've shown are the top 5 in 2006. This red line is buffer overflows. And in absolute numbers, it increases slightly over this time period. But in relative importance, it drops dramatically. The blue line is cross-site scripting. Then we've got SQL injection, PHP inclusions, and directory traversals. And what you notice is in 2005, the top 2, and in 2006, the top 3 most reported vulnerabilities are specific to web applications. So let's look at basically how does SQL injection work. So at a high level, if a user provides some malicious input and the application server fails to validate it sufficiently, then it may send a query that has the malicious intent from the user. And what can it do? Well, first it could return confidential information that the user was intended not to be able to see. Or it could start dropping tables and effectively destroy your database. So that's a nice story, but how about in the real world? Well, in 2007, of the web-based attacks that made the press, 20% were SQL injection attacks. And of those that were information leakage, this graph shows how many records were leaked per attack. So this is a log scale on the bottom, less than 1,000, 1 to 10,000, 10 to 100,000, and greater than 100,000. So the message here is just that these are out there, they're happening, and they're severe. Now, how about cross-site scripting? Well, there are several ways this can work, and I'll just present one. So suppose some user provides malicious input that then essentially gets stored as data on the database. Then some other user, through a normal query, gets that back in the web page. Well, what could happen? One thing it could, if the user is logged onto his bank account and has a cookie that has session identifier, that could be sent off to the attacker. So now the attacker can access this user's bank account. Or it could start executing some malware on the user's browser. So again, how about in the real world? Well, in 2007, 12% of the reported attacks were cross-site scripting. And to give a sense of how severe these can be, what's come to be known as the Myspace Worm, in the span of 24 hours, infected about 1 million systems. And that's dramatically more than any of the previous malware seen to date in the same time frame. So this is Code Red 1, Code Red 2, Slammer, and Blaster. Okay, so let me introduce this example that'll be a running example through a large portion of this talk. This is some PHP code, which is dramatically stripped down and simplified for an example. And it would live on the application server. And the setting here is an online shopping site where users browse, look at items, put items in their carts, and then eventually check out. And users are identified and linked to carts by session identifiers. So this code is getting the user's session identifier, passing it through the add slashes function, and concatenating that on to this constant string to form a query which gets sent to the database. I've shown this in red to show it's untrusted, coming from the user, and this in blue to show that it's trusted, coming from the application code. So if the user provides something like this string as the input for session identifier, then that'll get passed through add slashes, which just puts a slash in front of every quote and makes that string suitable to be included as a string literal, so that quotes get interpreted as quote characters and not string delimiters. But the problem is SID is not intended to be a string literal here. So this is the query that'll get constructed. And because of the low precedence of the OR operator, this 1 equals 1 always evaluates to true, and this conditional clause is true on every tuple, so that all of the active carts will get returned. Okay? So once again, here's where we're going. We're going to start with a generic and flexible characterization. Generic meaning you don't need application-specific knowledge. And the idea is you just take a query, and I can tell you whether it's good or bad. And then I'll speak about low overhead runtime checking, and finally, a sound and scalable static analysis.
Why selecting all cards wrong?
It's an information leakage. So the user, the application programmer intended the user to be able to see his own cart, but not everybody else is. I mean, it's a bit of a stretch, but you could imagine, I know this person's online and, is he looking at stuff he shouldn't be looking at, or some way I can get him in trouble or blackmail him. So, but that's sort of the basic idea with these information leakage things. Does that make sense?
Sure.
Okay. So, first the characterization. Now the problem here is that queries are being constructed as strings, structureless strings. And user input comes in as strings again. And there are a lot of ways you can regulate these strings. You can either, set up some blacklist that you filter out. You can escape quotes, like in the previous example. You can use regular expressions, and there are many others as well. The problem is each one of these treats the user input as isolated lexical entities. And the filtering or modification is done in order to enforce some kind of a syntactic property of the query as a whole. Now, if you're working in something like Java, for example, there's the prepared statement API, which enforces that the strings that go through that API be used as literal values, string literals or numeric literals. But in some languages, like PHP, that doesn't ship as part of the default standard library. And even in a language like Java, the default is still just strings. So even programmers who write Java programs will still misuse it. And finally, queries or Ben.
So would it be fair to say that for Java programs, for instance, if you just have a simple static filter that disallows things that are not prepared statements, the problem goes away?
If you
only allow prepared statements.
Okay, if you
deprecate the other APIs and say that they're just not allowed at all, does the problem go away?
So good question. If you just use prepared statement API, is the problem fixed? And so first, of course, you can use the prepared statement API without using it, in the sense that you use string construction to make a query and then put it through this prepared statement API. You know what I mean? And so that's one problem. I'm also going to try to argue that restricts you to only using literals, which is certainly the common case, but it won't help you here, for example, if you have more structure coming from a file or a database. And what I'm going to talk about, I also want to think of as sort of an enabling technology that enables users to do what they don't traditionally do because the support is not there historically. Okay. So, characterization. Across the bottom here is the conditional clause from the attack query that I showed earlier. And across the bottom here is the conditional clause from a similar query, except made with an example of an expected input. And then above them is the parse tree according to the SQL grammar. And what you notice in the case of this normal query is that the entire user input substring parses under one non-terminal. So that substring and nothing else. Whereas in this example, there is no one non-terminal that has exactly that substring as its descendants. And this is how we're going to distinguish good from bad. Okay? So in order to formalize this, we need to be able to formalize what is a web application server.
On the previous slide, why is it not sufficient to just identify the cases where you have something like the right-hand side where the input is not a value being parsed?
So let's see. Are you suggesting do something like check that the untrusted part is only a single token, or
that it parses to a a value in the SQL grammar as opposed to the more complicated condition you suggested.
Okay. So if the query is constructed like this, where a value is what fits, then the condition you suggested, I think, will be met, right? Because a value is the only thing that can parse here.
It's hard to imagine input that wouldn't meet that condition. I mean, when would you want the user to enter input that would parse to a SQL expression?
Okay, so one example that I'll get to in just a moment, but I'll talk about now since you're asking this, is suppose you've got something where the user is allowed to see everything, but may want to filter things out so that not everything is shown. Something like a bug database, like Bugzilla. Then if the user were to supply predicates, that would be okay, right? It's not any leakage if the user sees everything. So, in that case, you might want something like that.
The issue is that then what the user wants is really application specific, right? In some cases, he might want predicates. In some other cases, he might want values.
Right. It's application specific, but the way that the query is constructed should leave the right hole. So essentially, if this is the end of the trusted part, and then whatever comes after is from the user, then the hole here is this. But the user couldn't put a semicolon, drop tables, blah blah blah, right? So if you can distinguish what's from the user and what's not, then you've got enough information from the application to apply this definition. Okay. Okay, so our application server definition, we're just going to view this as a function from n tuples of strings or inputs to strings or queries. And the only constraint we'll put on these applications is that they construct the output strings by concatenating together several substrings. And each substring is either a constant string from the application or some filtered version of an input. And so from our previous example, the user provided this one tuple of an input string, and the application produced this query, and we saw it did so according to these rules. So in order to give our definition, I'm going to define a valid sentential form. So sentential form, recall, is just a string of terminals and non-terminals that you can derive from the grammar's start symbol. And if the query is constructed by a web application, we'll say there is a valid sentential form if the sentential form is constructed by concatenating constant strings and single symbols that summarize the untrusted parts. Okay, so in this case, the non-terminal num. And optionally, you can parameterize this definition by selecting some subset of the terminals and non-terminals you want to allow that the user should be able to provide. And so we'll say a query is an attack if it has no valid sentential form. Okay? So this is something I sort of discussed already with Jim's question, but basically it allows you in something like, a Bugzilla-like setting where you want to allow more structured input but not unrestricted input. And you can, say, select this non-terminal to be allowed. Another question is, does this definition exclude legitimate queries? And so we tried to think about this. One possibility is, something like this, where skip is not a keyword in the SQL grammar or SQL language. It's just meant to represent code that doesn't do anything. And if it doesn't do anything, there's no reason it ought to be allowed. So that's really not a limitation. Another possibility would be if the query were constructed in such a way that there is no valid sentential form possible. So you've got this grammar production, condition goes to value, comparison operator value, and the user is expected to provide operator value. And we've never encountered this in any of the applications we've looked at. So we don't consider this to be a limitation. Okay, so how do we check at runtime? Well,
I still have a question.
yes.
So here's a very naive approach. Whenever one of these programs takes an input string that is going to be typed in by the user, they say, okay, this string must parse to this particular token.
Okay.
Okay. Now this is a very generic solution. All it requires is that whenever such an input happens, the user has to specify what form should this input be.
Right.
And then if your grammar is parsable nicely, then whenever you get such an input, you can actually verify that it parses to something like that, right?
Mm-hmm.
This is a very generic solution because you have the power to specify exactly what the input should be.
Right.
So is what you are proposing here one way to guess such specifications automatically?
In a way. So I guess the question is, could you just require that the input be parsable, under the SQL grammar using this non-terminal as the start symbol, essentially?
Yeah, exactly. Basically, the application writer knows exactly what he or she wants.
Right.
And they can just say it, right?
Right. So I guess one difference between that approach and the approach that I'm proposing here is that in general, you don't, let me see how to say this. In general, the context matters, right? So a string that does parse under a certain non-terminal, when you put it into a query and parse the whole query, may not be under that non-terminal, right? So if you have, a silly example is drop table users. If that's a string literal, then yeah, sure, it parses as a string literal, but it could also parse as SQL code if it's not in quotes. So that's why checking at the input site is not equivalent to checking in the context of the query.
Okay, well, I don't understand, but we'll do it later.
Okay.
Yeah.
Okay. So in order to check at runtime, the first thing we need to know is which part of the query came from the user. So we're going to use these metadata delimiters to track the input through, which I'll denote with those two symbols. And so we'll just pop them on there at the input site. And then the application will construct what we'll call an augmented query. Augmented because it has these delimiters in it. Then we're going to modify the reference SQL grammar to include these delimiters. And the productions we'll add will have this form. Some non-terminal goes to delimiter, single symbol, delimiter. Because recall, we want the input to be able to be summarized by a single symbol. And so then if we can parse this, parse the augmented query with the augmented grammar, then it's okay and we'll allow it. And if it fails, then if it's not actually an attack, then it's a garbled query, and we don't want to send it on anyway, so we'll block it. So let me explain how we did the research prototype to evaluate this. So we took SQL grammar, and we defined some policy of terminals and non-terminals, and produced an augmented grammar. And for this prototype, we were doing everything at the code level, not under the surface. That would be a different approach. But since we were doing it this way, we had to represent these somehow. And we don't have access to anything that the user doesn't also have access to. So we just use strings, and we escape occurrences of them within the input. Then we feed this to a parser generator and add just a little extra functionality so that if the augmented query parses under the augmented grammar, it returns the query without the delimiters. Okay, so then we can add this into our runtime system, and input gets delimited on the way in and checked on the way out, and the result set also gets delimited on the way in because sometimes it gets used in subsequent queries, and the page gets sent back. But the delimiters are stripped off at both sides. So this isn't exposed to the user or the database. So we used some test subjects, and the primary reason we used them was that they'd been used in a previous evaluation of a technique to deal with SQL injection. So there was another group that had produced inputs for them, and that's what interested us.
Which group was that?
That was Alex Orso, William Halfont, and there was a master's student whose name I can't remember, and he's actually the one who produced the inputs. And he'd, anyway, so the bottom line is it didn't come from us. And our results are as follows. So basically the 2 points I want to make here, one is that we allowed all the queries based on legitimate inputs and blocked all the queries based on attack inputs. So that means our definition doesn't have any obvious flaws anyway. And then it took about 3 milliseconds per query, and we weren't working hard to optimize. It's essentially the time of a single parsing. So the overhead is fairly low, and it's reasonable for many runtime systems. Okay, so now how do we check statically? I guess the first question, and this is probably an audience I don't need to work hard to convince, but why do static analysis? And at runtime it's easy to be precise, but statically we can detect bugs early, we can analyze code modules, and if we can determine that the input validation is sufficient, then we don't have to add a check for the whole query. And the state of the art here is static taint analysis, and this is a line of work where Ben has done a lot. And so what I'm going to say is just, I'm going to talk about primarily the advantage that this approach will have over static taint analysis, but there are advantages the other way too, and I can talk about those later on in the talk. So here again is our running example code, just abbreviated a little bit. And then here's the data flow graph, where the get SID is coming in, goes through the function into this variable, they get concatenated into the query. So roughly, static taint analysis will take the following view of the data flow graph. All values get abstracted to these atomic integrity values, either untrusted or trusted. And there's some source of untrusted input, and there's some set of functions that's designated as being sanitizers. And then you want to ask, and the meaning of sanitizer is whatever comes out or whatever gets past it is trusted. And so what you want to ask is, at the sink, is untrusted values, could untrusted values flow into the sink, or is it all trusted? And according to this view, everything is okay, because we've got trusted down here. But I showed earlier an attack in this code, so this represents a false negative. And this is the kind of thing that we're going to try and discover. So here's the goal that we want to take of the data flow graph. We will use as abstractions sets of strings where substrings have integrity levels. Okay? And again, we'll have some source of untrusted input, and because this could be anything, we'll essentially say it's sigma star, where everything is untrusted. And we're not going to define any sanitizers. We'll just have transformations, where ideally the strings in this set are exactly the set that you could get by passing the strings in this set through this function. And then again, we have some sink that's of interest to us. But rather than giving an immediate thumbs up or thumbs down, we want to check whether in this set there's a string that according to our definition is an attack. And if so, we say the code that this represents has a vulnerability.
policy?
The policy is essentially what I showed earlier, where we want the untrusted part of the string to parse under a single non-terminal.
The same policy.
Same policy. Yeah.
So what is the integrity? Is that
The integrity, so high integrity or trusted means that substring came from the application code. Low integrity or untrusted means that substring came from the user.
so that integrity doesn't have to do with whether it parses under a non-terminal? It's orthogonal.
Right. So we're going to use that. We're going to use these integrity labels to determine which substrings.
You care about checking the policy.
Exactly.
Okay, so I can think of this is like a static instantiation of what you previously did dynamic.
Yes, exactly.
Okay.
So we're trying to check statically the property that we previously checked dynamically. Okay. And so in order to do this, we have to answer a couple of questions. How do we model the semantics of these string functions? And then how do we track integrity classes through them? Because in this case, it's easy. Everything's untrusted, so everything on the way out ought to be untrusted. But in general, that may not be the case. And then finally, how do we check this set of strings at the sink to see whether there's one that violates our policy? And so I'll address those questions in just a moment. First, I want to give a background on string analysis. So this comes from Minamide with his 2005 work. And he's going to use context-free grammars to model sets of strings. And essentially what he's going to do is take the data flow graph and work backwards to construct an extended context-free grammar, where this is the input, so it becomes a non-terminal, and it could be anything, so it'll be sigma star. And then here's another value, which will make a non-terminal from it, and just go backwards to make a new grammar production. And it's an extended grammar because it can include string functions. And what we're going to do is we're going to add integrity labels to the non-terminals. And the meaning of labeling a non-terminal as untrusted is that anything that derives from that non-terminal is untrusted. And so hopefully you can see that we are moving toward our goal here, where this is some set of untrusted strings, which can be derived from here. This is another set of untrusted strings, because anything derived from SID has to go through get SID. And so we're moving in that direction. Now, modeling string transformations. Finite state transducers are what we'll use to model string transformations. And so a transducer is basically an automaton with output. So there's the strip slashes function basically does the opposite job of add slashes, where add slashes puts a slash in front of every quote, strip slashes removes it, like in this example. You give this input string, O/quote Brian, it gives this output string. And so here's the input symbol and the output symbol. You read slash, output nothing. You read quote, output quote. You read slash, output nothing. Read anything else, output slash, whatever you just read. So that's how this transducer is modeling the semantics of this function. And we're going to use these transducers to change this extended context-free grammar into a standard context-free grammar. And essentially the idea there is we take the grammar that's rooted at the argument non-terminal and find its image over the transducer that models this string function. Okay? So how do we do that? Well, the algorithm for finding the image of a grammar over a transducer is very similar to the algorithm for finding the intersection of a grammar and an automaton. So here's an example grammar and its language, and an example automaton and its language. And the way the classical algorithm for CFL reachability works is you take a grammar production and you try and match its right-hand side to some transition in the automaton. And if you can, you add a new transition and label it with the left-hand side. And we'll put the subscript on there designating state from and 2. And then we'll just record that we added something with this label because of something with that label over here. Yes?
To represent a set of valid strings, do you really need the power of context-free grammars? Do you know examples where you can't express it with just automata?
So that's a good question. Do you need context freeness? And so the answer is yes and no, where there are program constructs where you need context freeness, where having that power will give you a more precise representation than regular languages. But I haven't seen examples where having the power of context freeness enables you to avoid some false bug reports where regular languages would produce false bug reports.
So what is the comparison complexity? If you take the image of a regular language with respect to a transducer, regular transducer, is it less complex, worst case complexity, than, say, taking the image of a context-free grammar with respect to a regular transducer?
What's the complexity difference if we were to use regular languages to represent sets of strings? So it's basically just think of intersection. So this is classically a cubic time algorithm, but at this last popple it was pushed down to n cubed over log n. And then to find, if we were instead using regular languages to represent sets of strings, it would be essentially automaton intersection, which is quadratic. Right. So continuing to run through this example, we'll match sigma to 0 through 9 and add a new transition labeled x and record that here. And then again, we can match sx here, and we would add a new s transition here, but we already have one. So we won't add anything here, we'll just record that we could have done it down there. And so hopefully what you can see is we've just constructed a grammar whose language is the intersection of these two languages. And so the difference, if this were a transducer rather than an automaton, is we would match on the input symbol and record on the output symbol. Okay? So now suppose our input grammar has integrity labels on the non-terminals. Well, hopefully you can see there's a direct correspondence between the non-terminals and these grammars. So we just copy them over. So now we've got the semantics of string functions, and we've got how to track integrity labels through them. Did you have a question? No? No. Okay. So how do we check policy conformance? Well, the algorithm we used is more involved than I'm going to get into here. But essentially, we want to take the SQL grammar as the reference grammar, and the grammar that we've generated, and check, whether there are languages in our grammar, whether there are strings in our grammar that don't parse as we'd like them to according to the SQL grammar. So here's our running example again, and this regular expression represents the image of sigma star over add slashes. And so let me just sort of walk through how we would do it on this example. So first we ask, can this non-terminal occur in a quoted context, that is, following an odd number of quotes? And the answer here is no. It always follows an even number, namely 0 quotes. So then we'll ask, can only numeric values be derived from here? And again, the answer is no. And then we can ask, can we derive some example SQL from here? And the answer is yes. So we know that in this grammar, there are attack strings, and hence the code that it represents has a vulnerability. So we have...
I guess I missed this, but could you talk about how you map from, how you convert from essentially a piece of code that represents remove slashes in this case to the formalism that you use?
Yeah, so how we move from the code to the formalism. So in writing the analyzer, there's an upfront cost where you have to write transducers for the library functions because you don't have code. And then after that, everything is automatic.
How many library functions would you estimate you need to write code? I mean, the specification for essentially.
Yeah. How many library functions? There are probably, I will say about 60 or 70 where it's useful to have good specifications. And then there are a couple hundred where you want at least the type specifications. So this function takes this type and returns that type. And more precision than that doesn't matter.
That's a fair amount of specification, right?
Yeah. Yeah, it's a fair amount of upfront work. Okay. So, fortunately, Minamita had done a lot of that upfront work. And he had written this PHP string analyzer, so we took that and we modified it to do what we wanted to do. And we got 6 real-world PHP web applications. So this is one of those things about being in academia is you can only get what's open source for the most part. And with PHP, there are real-world applications that are open source. With Java, it's sparser. And if you go to C#, then it's pretty sparse. So I wanted to make basically 2 points here. One is that we scaled up to almost 170,000 lines. And from what I've seen of PHP, the biggest I've seen is over 300,000. So this is pretty good. The string taint analysis is the time taken to generate the grammar. The policy conformance part is the time taken to check whether this grammar has strings that are attacks. And this example, tiger, is one that people ask about because it stands out. And the reason it took longer was it made extensive use of regular expression functions. So it would have a whole bunch of them in a row, sometimes in loops. So the result was it produced a very large grammar. And sometimes if there was one untrusted non-terminal coming in to some transducer, there will be multiple untrusted non-terminals coming out. And so that's why it took so long over here. We check each one individually, and if the surrounding context is big, it takes a long time. And the false positive rate was fairly low. In most cases, we got more real bug reports than false ones. And even when that wasn't the case, there weren't so many false errors as to overwhelm the user. And so let me just distinguish here. Direct means that the user provides the data directly, like through get or post parameters. Indirect means the string is coming from, say, a file or a database query where perhaps an untrusted user could modify what's in that database. We don't know. And so we did not distinguish between true and false bug reports here because the programmer may say that, I know that what's in that database is okay, so I don't have to check it.
Question. So do you have any way of ranking the errors? Because what we found at Microsoft is, it's not so much what your false positive rate is, but what's the top 5 things that you listed? If they're all false, it doesn't matter that the next 20 are all real because the developer will stop using your tool right there.
Okay, ranking bug reports is not something we looked at, but that's an interesting question. And I haven't thought about that one.
I wonder if you can comment on the complexity of the bugs you find, for instance, for Caroline. So it looks like the policy conformance time is low, which leads me to guess kind of that maybe they are actually fairly easy.
Yeah. So definitely the common case is that user input ought to be literal values, either numeric or string literals. Of these real bugs, there were 5 that. Let me see. So there were 5 of these where the data was being passed through some function, which, depending on how you would write your taint analysis, might be classified as a sanitizer. And so that sort of increases the complexity. But you're right, in most cases, the complexity was not too high. And this, I think, kind of says more about that, where I said that, there are some cases where the data is passing through some function. And so here's an example vulnerability that we found where the user ID is coming in through this get parameter. The code checks whether, in fact, that has been provided. If so, it assigns it here. And if not, it assigns empty string. And then ereg I means case insensitive. Ereg means, does this string value, is it in the language of this expression and not? So if it's not in the language of that expression, error message and exit. If it is, keep going and put it in the query down here. So do you see the vulnerability here? This was one where I had to sympathize with the programmers because I would have made the same mistake. So the problem is they forgot the anchors. Caret to match beginning of string and dollar to match end of string. So all this is checking actually is there a digit in the user input string? It's not checking whether it's numeric. So if the user has a digit here and anything else, it would get included. Okay, so cross-site scripting, and I just want to talk briefly about our characterization and our static analysis. So I gave this sort of hand-wavy example earlier, and I want to add a little bit more flesh to it, just to make it more concrete. Suppose you've got a classified ads setting, something like Craigslist, where users can list items for sale. And somebody lists as their item for sale this script, whatever, and it gets stored on the database. And then somebody else wants to know what's for sale, and so they get this back in the web page. And now some untrusted script is executing on their machine, and it could do bad stuff. And I claim this is a harder problem. And so I'll explain why that is. Harder to deal with than SQL injection. And part of the reason it's a harder problem is consider the earlier days of the web when there was much less active content and these pages were, HTML documents. And if something isn't written quite correctly, would you rather see a parsing error or most of the page with perhaps something a little garbled or not looking quite correctly? Well, certainly most people would rather see as much as possible. So web browsers were written to parse HTML permissively. Okay, so in some cases, closing tags are not needed. In some cases where only white space ought to be accepted, any non-alphanumeric characters are okay. Sometimes new lines are skipped, and there are many other examples. Also, many browsers support browser-specific tags or attributes which may be scriptable. And what all this means is, when you're given an HTML document, it's not easy to look at it and determine what in that document, how will the browser parse it? How will the browser interpret it? And what will fire up the JavaScript interpreter? So here's the policy that we're going to use. When the application server sends back this document, again, it perhaps constructs it as a string, and if something untrusted causes the client's JavaScript interpreter to fire up, we'll consider that cross-site scripting. So we're not going to try and analyze this JavaScript. And to describe which substrings will cause the interpreter to start, we examined the W3C recommendation, which is the HTML standard, as well as the Firefox source code, since we had access to that. And we produced a regular language that says, here are the strings that will start up the JavaScript interpreter. Okay? And so we modified our static analyzer from the previous step. And again, we found lots of cross-site scripting vulnerabilities. So I'm not going to talk about those here. But what I do want to talk about is this other finding, where in many applications, there's one function that performs all of the input validation, say all of the HTML input validation. And so we took several PHP applications and we manually identified one such function. And then we manually examine these functions to determine, do they intend to allow some HTML markup, like the bold tag or the italics tag. And then we analyzed each function in isolation. And what we found was all of those input validation functions that allow any HTML fail to prevent cross-site scripting. So this shows that it is a hard problem. It's hard to write these things. It's hard to get right. We need better ways to write them, and we need better tools to check them. So I think, okay. So just to recap at this point, I've presented a generic characterization, first of SQL injection and then of cross-site scripting. I talked about a low overhead runtime approach for SQL injection and a sound and scalable static analysis. That is the first that will find these kinds of vulnerabilities. So I think in the interest of time, I'm going to skip the next part and go to future directions. So broadly, I'm interested in software security, quality, reliability. And I like to address real-world problems because I like the work to be well-motivated, to have potential impact. And I'm interested in these newer domains. And I think this web application domain is still very rich. There's still a lot to be done there. So one thing that I know Ben has done some work on, and I've also got some ideas on, and I'm interested to address, is web worms. And the idea there is basically that defaults are hard to change. So no matter how good we are at finding cross-site scripting vulnerabilities, there will always be some. And the analogy here is with buffer overflows. Hey, no matter how good we are at detecting those vulnerabilities, there will always be some. So how do we deal with the reality that follows? How do we detect malicious JavaScript? How do we contain it? Another thing I'd be interested in is end-to-end analysis, specifically in terms of information flow. So if you've got, say, a medical record system, you want two people to be able to log in, and one person should be able to see some confidential information and another should not. And so you'd like to be able to know whether certain unintended information flows are possible. And this could require a multilingual analysis, since these are multi-tiered systems. And you have to deal with dynamic code. And ideally, you'd like it to be modular, so that if you switch out one part of it, then you can reuse most of the analysis.
What do you mean by dynamic code?
Dynamically generated, or code that generates code. Another thing is concurrent JavaScript, where what we see is that these handheld devices like cell phones and BlackBerries look like they're becoming the next frontier for web browsing. And they have power constraints. The result is that we'll expect to see multiple low-power processors rather than a single high-power processor. And currently, JavaScript's concurrency policy is when a thread starts, it runs until it's done. There's no interleaving, there's no preemption, nothing. And so what's the best way to add some concurrency in? And how can we deal with the dynamic or the metaprogramming, that is code-generating code aspect of JavaScript, which is used in practice?
How would JavaScript implementation ensure that?
Ensure?
This idea that a thread runs until it ends, and only then another thread runs.
Well, so that's the interpreter's responsibility, and I don't know the internals of the interpreter, how they're written, but I just know that that's the policy, and I am not familiar with cases of interpreters failing to do that correctly, although there may be. I'm also interested in dynamic languages, which is closely related topic. So, for one example, in Firefox, JavaScript and C++ are sister languages, where a component written in one could be replaced by a component written in the other. And programmers often think in terms of C or Java because that's the training that most programmers have. So what are some tools that will help developers or testers who are writing these things? And what are some language features or annotations that may help tools? So that's the end of my presentation. If there are questions, I'll be glad to take them.
So about these false positives, is there like some? Can you give like some cases where the tool will give these false positives, like, especially often, or where do they come in general? Is there like a clear cut?
So most of the false positives from our static analyzer come from false paths. Either, there's something like conditional here and then merge and another conditional, and all 4 paths are not possible, but the analyzer supposes they are. So we didn't have any false positives due to imprecision of the policy checking part. All of them were due to the imprecision of the grammar generation, where it's generating a grammar that has too much in its language, values that the runtime system would never produce.
So it's kind of pretty hard to write any kind of filter to remove those.
It may be. So the analysis is context insensitive, though flow sensitive, and so it perhaps could be improved by adding more context sensitivity. But yeah, right, at the cost of scalability. That's exactly right.
Do you know of attacks? I mean, that would not basically, that your policy would not be able to filter out, so to speak?
Attacks that our policy would so sort of false negatives of our policy. With cross-site scripting, we don't claim soundness because we were not able to examine the Internet Explorer source code, and Internet Explorer, has its own way of parsing. So there certainly are things that will invoke the JavaScript interpreter in Internet Explorer that wouldn't in Firefox and that wouldn't according to the HTML standard. So that's just sort of an incompleteness of what we had access to.
I was thinking more of a well-formed SQL expression that would match basically the grammar constraints that define your policy and
Okay.
still be basically able to leak some information that you would not.
So are there attacks that our SQL injection policy wouldn't catch? And I guess one class of attacks are expensive queries, where suppose you put a big expensive subquery in there, and it takes a long time to execute, and it effectively becomes denial of service. Beyond that, haven't found them.
Even how could you formally formulate that question? I mean, what's really the end game of what's harmful, and then prove that this criterion is satisfied? Are the other ways to just look at existing attacks and see if they are filtered out or not?
Right. So that's a good question. Yeah. So essentially, I think the question is there something that we could prove our definition correct with respect to? And I mean, at some level, you just have to give some axioms. And we would love to be able to prove it correct with respect to something, but as well as we can do, this is the thing that other things that like analyses are being proved correct with respect to, and you'd need some formal notion of correctness either for queries or for web applications, but that's what the definition is. So we'd love to be able to do that, but I don't think that's within the realm of possibility. If you have any ideas, I'd love to chat with you.